So, infants who cry more easily. This is chapter 14, example 14.1, and this is kind of our big one for this chapter. May be easily stimulated, infants who cry easily may be more easily stimulated than others, and it may be a sign of higher IQ. Child development researchers explored the relationship between crying infants 4 to 10 days old and their later test IQ scores. A snap of a rubber band on the sole of the foot was used to cause the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ using the Stanford Binet IQ test at age 3. They did it on these 38 infants. So in the past, we've made a plot, found the intercept, etc. We've made the numerical model. We've found an R value. This one happens to have an R value of 0.55 and an squares regression line of y hat equals 91.27 plus 1.493x. So the number of cries is about a 1.5 for each additional cry. According to this model, you get about 1.5 extra points on an IQ test. Okay. Notice this R squared. Do you remember what R squared means? R squared is the percentage of y that can be predicted by x. So this is about 21%. 21% of the intelligence can be predicted by how much they cry as an infant. It's not super high, but it's also not. Like, you look at this and go, this doesn't fit a line particularly well. What we're testing is does it matter at all? So this is clearly not a kid cries more, they are way more intelligent. No, but it might show you something. And it's hope for parents that have to put up with kids that cry a lot. So what we're going to do is test, is this just random chance that we got? And the only thing we're going to test is the slope. We're not going to do this for the y-intercept. We're testing, is the slope significant? Meaning, is it not 0? Okay. Or is there a possibility this is just random chance? And so instead of a plus bx, instead of this being y hat equals a plus bx, we know the true regression line for all infants is mu of y equals alpha plus beta x. But we don't know what that is, right? Our data gives us an estimate. So what we're wanting to know is how good is that estimate? Does that make sense? So essentially we have this line with a normal curve on it. Our regression is normally distributed with mean at beta, mean slope of beta. That makes sense? We know all the lines should fall within a normal distribution because they're average. You essentially have an average line. Part of calculating that least squares regression line is effectively like averaging. I I would the line falls within our data falls somewhere within a normal distribution relative to the line. Now, the normal distribution, yeah, I mean, the y-intercept could change the slope. It's not going to look exactly like that picture because it could be, less steep where it's going to cut through like this. But what we want to think about is it falls within the slope is norm the mean slope is normally distributed about the true regression line. That makes sense. It's hard to think of it and picture it on the graph. But if we think about the slope as slope is your x-axis. No. Yeah, slope would be your x-axis and it would be normally distributed within there. And if that normal distribution, if it's zero, we consider that no correlation. Anything having a slope of zero, we consider to have no correlation. If their slope is non-zero, we consider it to have some correlation. And that's what then the r and the r squared comes in. It's not just straight up how steep is the slope because it could be poorly correlated, but very steep, or really strongly correlated, but not that steep of a slope. So that kind of makes sense. Um, do you remember residuals? Y minus y hat. So a value minus the predicted value is the residual. That ring a bell, Noah? So the standard error about the line, and you're never going to calculate this by hand, is 1 over n minus 2 times the sum of the residuals squared. Or the square root of 1 over n minus 2. I'm not sure why it's n minus 2 this time, but it is. I'm sure there's a proof of it. Degrees of freedom is n minus 2. So data points minus 2, we had 38 in our first example, so degrees of freedom is 36. So here's our first infant studied, had 10 crying peaks at an IQ of 87. We can get a residual of negative 19.2. Here's a printout of all those residuals. You can square them, sum them. We could do this on our calculator. When you do the regression, you get a list that's stat.resid. So let's go ahead and do the regression on this. And mostly this is a learning thing. You'll let it do it for you later, but I want to add got my data here entered. I want to add a calculator page. There we go. Menu, statistics, stat calculations. We'll do it A plus BX because that's the form they like in stats. Menu statistics, stat calculations. Hmm. So now I'm just going to type that formula in. Square root 1 n minus 2 is 36. So I'm just going to put it in. The sum, I think the sum is here. Yeah, there it is. If I type stat dot, it'll give me all the options for what it calculated when it did that regression. That did not work how I thought it was going to. Like this. I think I can do just sum. That the value we're looking for. Yeah, 17.5. I guess it didn't like my sum notation. So you can just type sum on these calculators and to sum a list. It works on every Inspire. The coding is the same. The user interface just looks slightly different. Kind of handy little thing that it stored all that list of residuals, isn't it? Does that make sense? How I did this, essentially a little bit of programming. Since it stored that little list, all I'm doing is saying, taking the math notation and doing 1 over 36. I didn't do 38 minus 2, but you got to plug in for n. And then sum the list of the residuals squared. Do you know why I'm summing them squared? Squaring them makes them positive, so we square them, sum them, square root them. So that's partly why this formula is what it is. So, looking at the regression slope, your general formula, which again, we'll let the calculator do all these calculations for us. Most of it, we don't even have to do any programming like that. Or your general formula, though, for the slope, or for a confidence interval for the slope, is your predicted value B from your regression. Our regression gave us 1.5 plus or minus T star. So if we want the 95% confidence interval, we'd pick the T star for 95 with 36 degrees of freedom. times SEB, which is what we just calculated as 17.5. No, wait, no. What we just calculated was S. Okay. What we just calculated was the S there, not SAB. It does not go up and down 17.5 for each one. So mostly you'll get outputs for these things. Um, SEB, so if you're looking at these outputs, SEB is this thing right here. It's the standard deviation for, you have two things here. You have constant and you have cry count. Your equation for your line was X was the amount of crying they were doing, right? So that's cry count. The coefficient there means this is my slope, or B. This is my SEB. So you're taking T star, which for 95%, I guess you could look this up in the table, 32.042. And you could calculate it by hand. Or watch this. We grab our calculator. If you have all the data, what's important is that you know this formula so you can use it if all they give you is this output. That makes sense? You guys are comfortable looking up the T stars? Okay, that's what I thought by now. So if they don't give you the formula, if they give you the data like we did here, I should clear this. Menu, statistics, stats tests, linear regression t-test. Oh, actually, we're doing a confidence interval, sorry. Linear regression t-interval. We're looking for our regression on our interval on the slope. The menu confidence intervals. Oh, 95. I didn't even think about that. It just confidence intervals, linear regression t-interval, slope. It defaults to 0.95. Usually is going to be 0.95. So notice we have our B here. We have our A. They're kind of spread out. Degrees of freedom was 36. Our S value that we calculated was 17.49. Our SEB that I was just talking about right here, standard error of slope, 0.48. We have our R squared, that's useful, and our R. But then at the top of this, we are 95% confident that the slope is between 0.505 and 2.48. The slope between a child's cry count and their and later intelligence. 0.5 is not particularly much slope here, but it is not nothing. That if we took any sample, we're 95% confident that the true population, the more you cry as a kid, the more intelligent you are. It's not a huge predictor, but it is a predictor. Dylan, are you awake? Okay, does that kind of make sense? Let's look at it with a test. From the perspective of a stats test, we're testing for a t-value and you use B over SEB. Here, our B was like 1.49 over 0.04, not 0.04, 0.488. So our T is somewhere around 3. They have it below, it's 3.07. For 36 degrees of freedom, that's significantly less than a 0.05. If I look that up in the back of the book, I can look up 30.307. That's less than a 0.0025. There's a very low chance that this was random. Okay? That makes sense? Pretty sure this is an indicator. It doesn't give the kid intelligence, but it's just an indicator of later intelligence. But it's also not, again, keep in mind your R squared's only about 21%. So it's not nothing, but it's not a major predictor. There's probably other ones. Probably a better one would be the intelligence of the parents. Is probably a, but none of these are 100% predictors. And yeah, they give you some clues. Okay, our last one is going to involve drinking. We're going to talk about beer versus blood alcohol. Yes, welcome to stats class where we use non-school approved topics. You guys are going off to college soon. It's good that you know that this exists. How well does the number of beers a student drinks predict his or her blood alcohol content? 16 student volunteers at Ohio State University drank a randomly assigned number of cans of beer. Sure, they had a hard time getting volunteers for this, especially at Ohio State. 30 minutes later, a police officer measured their blood alcohol content. Here is the data. So, we're not going to put this into the calculator because they gave us a printout. So I want to make sure we know how to use the printouts. Because you would run the linear regression t-test just like you ran the confidence interval. That makes sense? Except you'd go stats tests instead of. So here we have beers versus blood alcohol. The student number doesn't matter. R squared is 0.800, meaning 80% of the student's blood alcohol content can be accounted for simply by the number of beers they drank. There are other factors like size. The bigger you are, typically, well, the alcohol doesn't affect you as strongly because there's more of you. So it's a lower percentage, is usually the case, but they're showing that 80% here is simply based on the amount of beers you had. So that's the, I'm sure, the strongest predictor. So the scatter plot shows the relationship. The students were equally divided between men and women and different in weight and usual drinking habits. Those things that also account for the blood alcohol content. Okay, all of those are generally considered factors. Because of this variation, many students don't believe that the number of drinks predicts their blood alcohol. Well, this line gives a fairly decent one. Um, about 80% of the variation in blood alcohol content is predicted by the number of beers. That is to say, the student's opinion is pretty much wrong. 5 beers produces an average blood alcohol content of 0.077, very close to the general driving limit of 0.08. Okay. These were probably also very weak beers. When this was done, there's a lot of high alcohol content beers that are out there, more popular, and micro brews and everything that was not as popular. So, yeah, these are probably low end. I would not take this to be fact. So, we're going to test our hypothesis that the mean number of beers has no effect on blood alcohol content against the one-sided alternative. So, we're going to test H naught beta equals 0, the slope equals 0, versus it's greater than 0. We're not going to bother being two-sided that it could be a negative slope. Beers would reduce your blood alcohol content. That doesn't even make any sense. Um, it is no surprise that we get, so to do our calculation, we get, notice this, it gives it to us right here. Our t value is 7.48. It has a p-value that rounds off to 0. So there's basically no chance that beers does not affect your blood alcohol content, the number of beers. Like, yeah, it doesn't take a genius to know this. Notice our standard error. This is our SEB value. Very, very low. The slope isn't significantly high, but I mean, a lot higher than this. So, yeah, one beer doesn't take you over the legal limit for most people. And their average here had 5 doesn't. Okay. Our regression line and our confidence interval would give us an interval for the mean. Okay. What's going to happen tomorrow is we're going to talk about a prediction interval, which would give us an interval. A 95% prediction interval would give us an interval for the general individual person. Okay. So our confidence interval, and we can put this into our calculator, we'll do it tomorrow, can give us the overall, but there's something called a prediction interval, which will be bigger, which will give us a 95% prediction for an individual, not for a mean of a group. That makes sense? Okay, that's 14.1. Hope that didn't feel that bad.